Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nabi Ifan bin Muhammad Amin. My metric ID is FB24051. We are from Group 2 and we will present to you about our ANN simulation project. So our group choose project 7, which is multi-sensor fusion for machine health monitoring. This project is prepared for Professor IR Dr. Ahmad Razlan bin Yusuf. So this is our team members, which is the first one is Ahmad Akib bin Muhammad Azri, FB24050, as seen in the picture, and myself, Muhammad Nabi Fan bin Muhammad Amin, FB24051.
Alright, so for the problem overview by industrial motivation site, which is the first one is the cost of unplanned downtime. There are unexpected failure of critical components in CNC machinery that could cause global manufacturing industries around billions annually due to halted production lines and secondary mechanical disruption. So the second one is flaws of some traditional maintenance, which is the equipment may require fixing after a breakdown that could cause yield of high repair costs and severe logistical bottlenecks. The third one is the single sensor bottleneck. The condition monitoring system (CMS) usually track a single physical parameter, for example, the vibration or amplitude. This approach completely miss multi-model signatures, leading to high false alarm rates, around more less than 40%, and miss internal thermal or electrical faults. So the fourth one is preventive maintenance, which is time-based schedules frequently lead to over-maintenance or premature component replacement, wasting perfectly functional assets of the machinery. Alright, so for our project objectives for the multi-sensor fusion for machine health monitoring, which is the first one is we could implement multi-sensor fusion framework. So this basically break reliance on isolated sensor by synchronously blending four distinct physical phenomena, which is mechanical, dynamics, thermal distribution, and electrical load modulation, and microstructural stress waves. So the second objective is to develop high fidelity physics guided simulation environment. So this product could build a robust, scalable simulation engine capable of generating realistic multi-variable CNC health degradation datasets without disruptive testing on expensive industrial workshop hardware. So the third objective is to construct a multitask artificial neural network. This architect a unified deep learning network to simultaneously predict the time health percentages. All of this could classify the precise root cause among seven operational states and quantify the fault severity level. Alright. So for our simulation framework, it is based on physics informed rationale. Physical CNC operations are usually backed by distinct deterministic equations. Common pure data driven model basically lacks safety guardrails. So our dataset incorporates the mathematical formulation represented through component mechanics. So there are four type of synthetic signal modeling foundation that we use, which is vibration signal that could model as a sequence of localized periodic impact forces by structural damping coefficients and random high frequency Gaussian white noise. So the second signal, which is thermal signal, it is account for fractional heat generation at high load spannings that could basically against ambient heat dissipation. The third one is electrical current. It is modeled by overlaying periodic loop current ripples and total harmonic distortion expressions onto the fundamental motor drive frequency. The last one is acoustic emission. It is generated by as a transient high frequency stress that could release the waves by micro cracking events, modeled via decaying sinusoidal burst signal. Alright, so for the operating conditions and scenarios, to make sure that our model could generalize across the realistic machining operations and some boundary conditions, we usually set the spindle speed dynamically within a wide envelope of 1000 to 3000 RPM. So the process enablers, we use variable tool feed rates by shifting the depth of cut and fluctuating external torque loads. There are seven comprehensive class for profile metrics that we usually use, which is the first one is normal operation to set the baseline benchmark. Second one is bearing inertia defect, which could impact the mapping to the shaft frequency. The third one is bearing outer race defect that could impact waves tracking the ball pass frequency. Fourth one is shaft imbalance by synchronous the rotational frequency amplification. Fifth one is structural misalignment to ensure directional, axial, and radial structural stress signatures. Sixth one is tube breakage or chipping. This is to avoid sudden or severe transient energy spike in vibration and acoustic emissions. Last one is lubrication starvation. There are some conditions that thermal accumulation combined with high frequency acoustic friction noise. Alright, so next slide is feature extraction pipeline. So the first one is high dimensional time domain feature engineering. So this is extracted directly from high frequency raw data arrays to isolate the structural patterns. So the first structural patterns, which is energy matrix, root mean square RMS to quantify overall structural energy and peak amplitude for extreme transient limits. Second one is statistical distribution, which is from kurtosis to detect impulsive fault impacts, the skewness or to gauge waveform asymmetry and crest factor to monitor early stage surface spin. So the second one is frequency domain and process contact extraction, which is spectral features from fast Fourier transform (FFT) uh, that is to peak tracking, current total harmonic distortion (THD) coefficients, and acoustic emission frequency centroids. For the process metadata, an ambient room temperature offset, active spindle RPM, and commanded feed rate vectors. Next is data compilation and quality control. For the total dataset volume, 1000 complete operational records of 200 for normal and 100 faulty, distributed evenly across minor, moderate, and severe states. For the pre-processing, we applied Z-score normalization across all columns to eliminate scaling bias and ensure stable gradient descent during neural network training. Alright, for the network architecture part, which is triple task ANN design. For the multitask learning paradigm, rather than running three standalone models, a single deep neural network utilizes a shared feature representation layer. This prevents overfitting, enhance calculation speed, and capture cross-task dependencies. There are three parallel dynastic outputs that we capture, which is first task is Haskell regression continuous. The output a single scalar value from 0% to 100%, representing the exact remaining hash capacity of the machine. Second task is fault classification, categorical. This computes a probability distribution over the seven operating states using a softmax output activation to output the single most probable root cause. Third task is severity assessment, discrete. Classify the active anomaly into four distinct actionable urgency bands, which is normal, minor, moderate, or severe. The picture explain the three parallel dynastic outputs. Alright, so for the mathematical and hyperparameter setup, we use layer topology configuration, which is a fully customized feed-forward deep neural structure. For the input layer, we use 40 nodes representing the complete multi-sensor engineered feature vector. For the shared hidden core, four sequentially dense hidden layers, which is 128 to 64 to 32 to 16 neurons, running hyperbolic tangent sigmoid tensor activation functions. For the mathematical objective formulation, we combine optimization loss via a weighted objective function. So the total loss is the ultimate error score network tries to minimize during training. For the mean square error, which is to calculate the error for our regression task, which is the continuous 0 to 100% health score. For the categorical cross entropy, which is used for the classification task, the seven fault types, and four severity levels to measure how confident the network is when assigning a category. For the training and regularization strategy, the optimizer is the Levenberg-Marquardt LM backpropagation algorithm for fast convergence. The generalization emphasis is backed by the Bayesian regularization and automated early stopping to halt training if validation loss diverge and guaranteeing the absolute immunity against the model memorization.
My name is Ahmad Akid bin Muhammad Nazri and my metric number is FB24050 and I will be presenting the result section. So first of all, we are going straight into the health score regression accuracy. So the R square score, which is 0.934, this has shown that it is high predictive fidelity for MAE, which is 4.62, and also for the reliability is 95%, which is for performance. So these predictions track the true health degradation with high fidelity, especially in critical states when the health is below 40 and mean absolute error remains well below the 5-point industrial threshold. So from this regression accuracy, tracking remains highly precise even during rapid exponential degradation phases, providing reliable early warning thresholds before failure occurs. So moving on to the next result, which is fault classification of our fusion performance. So as you can see from this graph, the comparison demonstrates a 19 percentage point improvement over single sensor vibration baselines. So the fusion advantage is that multi-sensor data fusion reached an overall classification accuracy of 95.3%. And for per class metrics, the normal state and shaft anomalies achieve near perfect precision, which is more than 97%. And for complex such structural defects, which including tool breakage or lubrication, maintain strong, reliable F1 scores, which is from 93.5% to 96.5%. So for the highlights of the confusion, minor misclassifications occur strictly between closely adjacent bearing faults, which is IR versus OR defects, during early stage low severity cycles. So the next is our detailed diagnostics for per class performance. As you can see, this is the value for each fault class, which include normal operation, bearing defects, shift imbalance, tool breakage, and lastly lubrication failure. And the provided values are perfect precision, recall, and also F1 score. So for the next result, which is permutation feature importance ranking. So as you can see from most of our runs, we can say that the VIB kurtosis is the most discriminative for impulsive bearing defects. And after that, we have the acoustic emission energy, which is critical early warning indicator for crack growth. And lastly, for the third after VIB kurtosis and AE energy is temperature bearing rate, which is the primary driver for lubrication failure detection. So from this, for permutation significant findings, vibration kurtosis and acoustic emission energy rank highest for isolating structure impact faults, which include bearings and tool chipping. And also thermal gradient slope stood out as the most dominant discriminator for identifying lubrication breakdown. And from this permutation feature importance ranking, the synergy proved that no single sensor dominated across all classes, validating the critical necessity of a combined multi-sensor approach. So as you can see here, this is the graph that will be generated when you run the permutation feature importance ranking MATLAB code and diagnostics. And lastly, for the result, which is sensor ablation study. So as you can see, this is the graph that will be generated from our MATLAB code for ablation study, which sensor modality contribution to diagnostics accuracy. So as you can see, the marginal contribution of a sensor groups to diagnostics accuracy. The baseline evaluation is vibration only models reach an isolated accuracy of only 76.3%. And for the incremental gains, combining vibration with acoustic emission lifted diagnostic performance to 88.2%. And for the full paradigm success, integrating the full site, which is mechanical, acoustic, thermal, and electrical, achieved the peak accuracy of 95.3%, highlighting a 90% boost over standalone monitoring. So now we are going to do a little demonstration of our artificial neural network system for our CNC machine health monitoring. So first of all, we are going to generate synthetic multi-sensor machine data. This M file will generate a dataset of 1,000 label sample across all 7 fault conditions using physics-informed simulation of vibration, temperature, electrical, and acoustic emission signals. So each sample contains 40 extracted features plus health score, fault class, and also severity label. So we are going to run this M file first to generate the 1,000 label samples. So as you can see, we have generated all of the 1,000 label samples across 7 fault conditions. So after we generate the data, we are going to train the fusion system. This M file will load the pre-generated dataset and trains out of the 3 networks. The first network being the health score regression, the second network being the fault classification through the 7 class, and the third network is for the severity assessment, which is for the 4 class. So we're going to run this M file to train our fusion system. So now it is training the 3 of our networks. So now it has trained our fusion system, and for all of our networks, you can see the accuracy for each test for each networks, and you also can see the performance summary. The first network is our health regression. The second network is for our fault classification, and lastly the third network is our severity assessment. So as you can see, it generates the fault classification confusion matrix. So as you can see, for normal 30, bearing 13, imbalance is 11, misalignment is 20, tool break is 27, and lubrication fail is 26. So it generates the fault classification matrix that we are going to later diagnose. So after we have done train our fusion system, we are going to see the real-time diagnostics. So we are going to run this M file. So this M file used the 3 trained ANN models to provide a complete 3-level machine health diagnosis from a set of sensor readings. So this also includes sensor fault detection, any missing sensor handling, and a live dashboard display. So we are going to run this. As you can see, the integrated diagnostics from the 3 trained ANN models that we trained just now. So as you can see, this is the overall machine health score, and this is the severity assessment based on the data that we got from the 3 trained ANN models, and this is the confidence for each diagnosis. So after that, if we want to check or perform 3 complementary importance analysis on the trained fusion system, we can run this M file. This M file will perform the 3 important analysis, which include permutation importance, that is going to measure our accuracy drop when each feature is shuffled, and it also will conduct sensor group importance analysis to compare per sensor group contributions, and also single versus multi-sensor ablation that will train individual sensor ANNs and compare against all the full 40 feature fusion system. So we are going to run this M file to conduct all of those importance in diagnosis. So this is our result from the importance analysis. So this is the ablation study for sensor modality contribution to diagnostic accuracy. So as you can see, this is the graph for the fault classification, which is single versus fusion, and this is the fusion improvement of a single sensor. So this is for the sensor group importance, and this is our permutation importance, the top 15 feature permutation importance in fault classification. And lastly, to fully display our machine health data diagnosis and analysis, we have this M file that will show and simulate the live factory floor with all 6 CNC machines, and each machine is diagnosed every refresh cycle using the already trained models that we trained previously. The dashboard will provide a fleet overview panel, per machine detail view, which is all of the 40 sensor gauges and 4 waveform plots, which are health score arc, fault severity labels, confidence bar, and it also shows the 7-day health trend chart per machine, and the alert log with simulated SMS or email notification stops, and lastly sensor diagnostic panel that detect stuck or noisy or clipping sensors. So this is the dashboard that we provided. So to interact with this dashboard, you have to click from 1 to 6 that will allow you to choose which machine that you are going to monitor. So we go into the first machine, which is our milling machine. So we just press 1 to access this dashboard. So as you can see, all of the graph and all the signal, this is all the all 40 sensors readings. And we are going to the second one, which is our turning. The third one being our grinding. The fourth one is our drilling machine. The fifth one is our boring, and lastly for the second operation of milling is our sixth machine. So you can see all the recent alerts from all of the machines, and you can also see the sensor status, the confidence of the sensor. You can see the fault type and the severity, and you can see all of the sensor readings in real time. So to quit this dashboard, you just have to press Q, and it will automatically close the dashboard. So that's all from us for our demonstration. Thank you. So now to conclude our presentation, I'm going to explain the core milestones of our project. One of it is that we have achieved our objective. We have engineered and validated a highly accurate physics-guided multi-sensor diagnostics paradigm, which is on 95.3%. And we have also proven that a multitask artificial neural network system has successfully handled regression, classification, and also severity sizing simultaneously inside a single runtime footprint. And lastly, for the technical takeaway, we have also demonstrated the sensor fusion resolve the fast alarm and also misdetection flaws inherent to legacy single sensor monitoring tools. So that's all from us. Thank you.